Hello, ladies and gentlemen. Mr. Dorfler here. Time for your daily dose of Dorfler, brought to you by me, free of charge for your enjoyment. Anyway, we are going to continue on in section 3 of chapter 7. In the first part of section 3, we talked about the atomic radius, ionic size, and the trends associated with that. And so we're going to pick up kind of where we left off in terms of ions with a term that you probably have never heard of before, and that is isoelectronic series. It's a very fancy name. Really, all it means is we have a group of ions or elements, if you will, that have the same number of electrons. Okay, and one thing we need to remember when we're talking about ionic size, if we have a set of ions that have the same number of electrons, we can determine the size of those and compare them between that group based upon their atomic number or nuclear charge. Okay, so the higher the atomic number in the group, the smaller it's going to be. And vice versa, the smallest number of the group in terms of atomic number, the larger it will be. So let's take a look at an example here. So we are to arrange the ions of potassium, chlorine, and calcium and sulfur in order of decreasing size. So we have to make sure we place our largest in the first and the smallest in the last position. Anyway, if you have your periodic table out, you're going to see that sulfur is atomic number 16, potassium is atomic number 19, chlorine is atomic number 17, and calcium, didn't know which one it was, is atomic number 20. Okay, if you count, sulfur is atomic number 16. It has a 2 minus charge. That means 2 electrons had to be added. So that means they have a total of 18 electrons. Chlorine has a 1 minus charge. Its atomic number is 17, so you have a 1 minus charge, means you had to add 1 electron, so therefore you have 18 electrons. Potassium is a plus 1 charge. It has an atomic number of 19, therefore, means we had to lose an electron, so it also has 18 electrons. And Ca2 plus, calcium has an atomic number of 20, and therefore lost 2 electrons and has 18 electrons present. So all 4 of these ions have 18 electrons. So we need to figure out the order in terms of largest to smallest. So what we need to do is identify which element has the lowest atomic number. That would be sulfur. Which one has the highest atomic number? That will be calcium. So going from the largest ion to the smallest ion, it goes sulfur, or I should say S2 minus. Next is Cl minus. The next one would be K plus, and the last one would be Ca2 plus. Okay, so first we have to identify if the grouping of ions is an isoelectronic series. So that means making sure, counting how many electrons they all have. If they do, then we can use the idea of ionic size by simply looking at the atomic number. Let's look at the practice exercise here. In the isoelectronic series, we have rubidium, strontium, and yttrium. So we have Rb plus, Sr2 plus, and Y3 plus. And we are asked to locate or determine which ion is the largest. Well, if you look here down on towards the bottom of the periodic table, element number 37, 38, and 39 is rubidium, strontium, and yttrium. So, do they all have the same number of electrons? Okay, rubidium is a plus 1. It originally had 37 electrons, basing it off the atomic number. It lost 1. That means it has 36 electrons. Strontium is a plus 2. It originally, in a neutral atom, has 38 electrons. Lose 2, you have 36 electrons. Yttrium, atomic number 39, means it has 39 electrons. Plus 3 means they lost 3 electrons, so therefore it has a total of 36 electrons. So these 3 ions are in an isoelectronic series. So who is the largest? Well, whoever the largest is has to have the smallest atomic number, which is rubidium at atomic number 37. Therefore, Rb plus is the largest ion. So again, really the main thing you got to do is when you're dealing with ions and talking about size, you've got to verify if it's an isoelectronic series or not. And from there on out, you can proceed accordingly. Okay. So our next topic, what we get into in section 4, is a term called ionization energy. Okay. We're also going to look at what happens when we do an electron configuration of ions. Okay. So what is ionization energy? Think about that. It's got the word ion in there, okay, and energy. So it's the amount of energy required to remove an electron from the ground state of a gaseous atom or ion. So it's the energy required to remove remove electrons to form ions. So that usually is associated with the formation of cations. And we have levels of ionization energy. The first ionization energy is the energy required to remove the first electron. The second ionization energy is the energy required to remove the second electron. I bet you can probably at this point gather what the third ionization energy is. If you guessed it's the energy required to remove the third electron, you win. So let's take a look at some examples here. Okay. Every time you remove an electron, it requires more and more energy to remove the following electrons. And so that's because as you are removing your first electron, you now have an imbalance of protons to electrons. You now have a greater number of protons, which are going to have a strong grasp on those electrons, those valence electrons. And also, you're going to lose repulsion between electrons. So, with each successive valence electron you remove, you're having an imbalance of protons to electrons. You just are allowing those protons to have a much stronger grip every single time you remove an electron. So if you look at some of these here, you see sodium, its first ionization energy in terms of kilojoules per mole is 496. So it takes 496 kilojoules per mole of energy to remove the first electron from sodium, okay? And as you see here, we're getting into more and more elements here. But then you notice that there's a little stair step happening here. Let's look at sodium, for instance. With sodium, it only has one valence electron. So after you remove that one valence electron, look what happens to its energy, of its second ionization energy. 4,562. Going from removing the one and only valence electron of 496 kilojoules per mole, you now take what they say a quantum leap to 4,562 kilojoules per mole to remove the second electron from sodium. And the reason why it goes up so incredibly high in terms of the required energy for this is because after you have removed all of the valence electrons, you are now dabbling in what we called the other day the core electrons. Now, the core electrons, I tell you what, they do not like to be messed with. They like their position. They don't like to go anywhere, and they are going to put up a fight. So the likelihood of you actually removing a core electron is very minimal, okay? So that's why you see these quantum leaps of energies required to remove electrons. It's because you're now dealing with core electrons, and that's a big all right? So let's take a look at these 3 colored squares from the periodic table, okay? We've got a red one, we've got a blue one, and we've got a green one. Of these 3 elements, we are to determine which one has the largest second ionization energy. So basically, which one of these 3 elements is going to have a second ionization energy dealing with the removal of a core electron. So what do we have? We've got red is sodium. If you look at a periodic table and line them up, red is sodium. Blue is calcium. And green is sulfur. So think about how many valence electrons each one of these has. Sodium only has one valence electron. We just got done talking about that. Calcium has two valence electrons. And sulfur has 6 valence electrons. So of these three, which would we expect to have the highest second ionization energy? Well, for this question, it would be sodium, because after you have removed the first valence electron from all three of these, calcium and sulfur still have valence electrons to give. Whereas sodium, you've already removed the one and only valence electron. So after you remove that valence electron, you now are dabbling in the core electrons. So it's going to have a humongous increase in the second ionization energy. So that's why for this answer, it would be sodium. So let's look at dealing with the remaining two elements, calcium and sulfur. Which one would have the greater third ionization energy? Well, again, third ionization energy means the energy required to remove the third electron. Calcium only has 2 valence electrons. Sulfur, again, has 6. If you were to try and remove 3 electrons from calcium, that third electron is going to be coming from the core electrons. And it, again, is a no-no. So its third ionization energy for calcium is going to be astronomical. And I wasn't certain if they had it on this table, but they don't. So, but just know that that third electron coming from the core electrons, not going to happen. So your answer for the practice exercise would be that calcium has the greater third ionization energy because the third electron is coming from the core electrons. All right, so let's talk about trends. So vertically speaking, as you go down a column, so top to bottom, your first ionization energy is going to decrease. Now, as you see here on this image here, they have the arrow going from bottom up as the increasing ionization energy. You can do it however you want, okay? So you can either put from top down, your ionization energy is going to decrease, or you could do bottom up and have your ionization energy increasing, okay? Now, for atoms in the same group, so the same vertical column, Zeph, or your effective nuclear charge, is essentially the same. But the valence electrons are further from the nucleus, meaning they're going to be a little bit easier to pick away from the atom. Because they are further away, they have less of a grip from the protons acting on those valence electrons. So that's why it's going to require less energy to pluck them away the further they are from the nucleus. Now, generally, okay, we see that word generally right now, and then we're going to discuss why they use generally. But generally, as one goes across a row, it becomes harder to remove an electron. So left to right, your ionization energy is going to increase. And that is because of your effective nuclear charge, or Zeph. Again, Zeph is basically the hold that the protons have on the valence electrons. And as we go left to right, your Zeph increases. So you are going to have more energy to remove electrons as you go left to right. So left to right, ionization energy increases. But there are two what we call discontinuities in this horizontal trend. The first occurs between groups 2A and 3A. So let's look at beryllium, which is 2A, and boron, which is 3A. Okay? The outermost electron in 3A is a single electron in a p orbital. Whereas in 2A, we've got 2 electrons filling out the s orbital, so it's pretty, kind of happy. So this this electron in the p orbital is further away from the nucleus. And what did we say occurs when electrons are further away from the nucleus? Well, it's a little easier to pluck those electrons away. So this single poor little electron all by itself in the p orbital is further away, and so therefore it takes less energy to remove them. But not only that, but these electrons in the s orbital are also playing a little sneaky trick on this lonesome p electron, and they're actually repelling that one single p electron. They're kicking them out. They don't want that, because honestly, with that single electron in the p orbital, it does raise the overall energy of an atom up slightly. And again, the lower the energy of an atom can be, the happier it is. So that's why we see the ionization energy in group 3A decrease a little bit as compared to 2A. The second discontinuity happens between groups 5A and 6A. So between right here where nitrogen is and where oxygen is. And this occurs because the electron removed comes from a doubly occupied orbital. Okay, in the terms of the group 5A where nitrogen is, each box in the p orbital has a single electron. But then when you get to group 6A, that first box in the p orbital now is doubled up. Okay? It is doubled up, and we get an increase in repulsion. And so you're going to see that the doubled up electron is going to be a little easier to remove from that scenario. And so that's why you see a slight, again, decrease in ionization energy in group 6 than you do in group 5. All right, so let's look at some examples here. Okay, we need to refer to the periodic table and arrange them. When I say them, I mean the atoms of neon, sodium, phosphorus, argon, and potassium in order of increasing first ionization energies. So, in order to solve this, we have to locate the elements on the periodic table. And we can do this solving without this fancy periodic table. We can just use a regular old two-dimensional periodic table that you've been given. So what we do notice is that sodium, phosphorus, and argon are in the same period. So in terms of ionization energy, we know that going left to right, our ionization energy increases. So just for looking at those 3 out of the 5 elements, excuse me, we're going to have the order in terms of sodium, phosphorus, argon. But that leaves us with potassium and neon. Okay? So neon is above argon in the periodic table. So using the trend, we would say that neon is larger than argon. So neon's going to be placed to the right of argon. Secondly, we see that potassium is below sodium. So that means it's a lower ionization energy. So therefore, it should be placed to the left of sodium. So our correct order in terms of increasing first ionization energy is potassium, sodium, phosphorus, argon, neon. Okay? Most important thing in this case is locate the elements involved. So our practice exercise says which has the lowest first ionization energy? Boron, aluminum, carbon, or silicon, and then which has the highest? Well, let's locate them again. Boron is here, aluminum is below boron, carbon is in the next group, and silicon is below silicon is below carbon. So looking at the locations of these elements here, let's first identify who would have the lowest ionization energy. Well, I guess if you look at this table, it's pretty easy to tell. But let's explain why. First off, as you go down a group, your first ionization energy is going to decrease, okay? So we therefore look at aluminum and silicon. We then ask the question, okay, what's the other trend? Aluminum and silicon are in the same period. So what is the periodic trend across a period? So as we said here, as we go left to right across a period, your ionization energy is going to increase. So with those two trends being looked at, our answer for which one has the lowest first ionization energy will be aluminum. So our next question is, who would be the highest? Again, use the trends. Okay, so we know that going down, top down, our first ionization decreases. So we look at carbon and boron, and we know that they are in the same period, and going in the same period, left to right, you increase your first ionization energy. And since carbon is to the right of boron, carbon will have the highest first ionization energy of these four elements. All right, we are getting down to the nitty-gritty, okay, of these sections here and towards getting close to the end of our video. But now we're shifting our focus to the electron configurations this time of ions, okay? And so we've done a lot of electron configurations, especially in the last chapter. But let's look at what happens and how we go about creating electron configurations of ions when we either add or remove electrons. So let's look at the removal of electrons. When electrons are removed to form cations, it always gets removed from an occupied orbital having the largest principal quantum number first. So that means the numbers with the largest quantum numbers, that is where we start pulling electrons from first. For instance, if we look at iron, okay, iron has a noble gas electron configuration of Ar4s2 3d6. If we were to make iron 2, which means we remove 2 electrons, those 2 electrons are going to be removed from the 4s, okay, because 4s is the 4 is the highest principal quantum number in the setup. So that means the 2 electrons get moved here, and we have a new electron configuration for the Fe2 plus ion of Ar3d6. But iron can also form iron 3. So that means if we were to form iron 3, which means we have to remove a single electron more, well, all that we have left is 3d6, which 3d6 would be the furthest or the largest principal quantum number in this case. And so we remove 1 electron from here, and we now get Ar3d5. And as you've probably noticed that in these 2 examples, they have plus 2e or plus e. That just shows us, the reader, that 2 electrons in the first example and 1 electron in the second example were removed. Do not worry about writing those out, okay? Pretend those don't exist. I don't need to worry about that. I'm more concerned that you can do the electron configuration of ions more than I am if you know how to put out there the number of electrons, okay? But what happens if we have elements to where we remove electrons, but we also have an s and a p orbital occupied, okay? If we look at tin, well, first of all, let's go back to the rule here. If more than 1 occupied subshell for a given value of n, meaning if we have like 4s and 4p, electrons are first removed from the orbital with the highest value of L, which would be p, and then we'd move to s. So tin, again, has a noble gas configuration of Kr5s2, 4d10, 5p2. Well, tin can form a 2 plus ion, okay? So that those 2 electrons are going to be pulled from the highest principal quantum number which has the highest value of L in it for its subshell, which P, again, has a value of L of 1, whereas S has a value of L of 0, those two electrons are going to be removed from the p orbital. So 5p essentially gets knocked out. And so our noble gas configuration for SN2 plus becomes Kr 5s2 4d10. But what happens if we go the opposite direction and add electrons? When we add electrons to an atom to form an anion, you are going to be placed into empty or partially filled orbitals that have the lowest value of N. For instance, if we look at fluorine, okay, fluorine has an initial electron configuration of 2s2, 2p5. And so if we were to add an electron, well, the only place that we can add an electron that isn't filled is the 2p orbital. Because again, p orbitals can hold 6 electrons. The s orbital, the 1s orbital is already filled. The 2s orbital is already filled. The 2p is all I got. So I add the electron, and now my new ionic configuration for this, for F minus, is 1s2, 2s2, 2p6. Let's do a couple of examples here, okay? And I'm just going to kind of look off of here before we get into our practice ones down here. Okay, I got some time. So what we're going to do is we are going to look at Ca2 plus, CO3 plus, and S2 minus, and do the electron configuration. So Ca2 plus typically has an Ar4s2 electronic configuration. But because it's a 2 plus, we have to remove 2 electrons. And the only place in this instance that we can remove the electrons are from the 4s. So honestly, you could simply remove that 4s2 and keep the noble gas of argon in the parentheses, and that could be your answer. That's it. Pretty simple, huh? But now let's look at cobalt. Cobalt typically has an electron configuration of Ar4s2 3d7. But cobalt can form a 3 plus cation. So looking at the original, the normal, or typical electron configuration of a neutral atom, 2 of the 3 atoms must come from the 4s, okay? Because again, it's coming from the highest principal quantum number. That's where they have to be drawn from first. So we take 2 from the 4s, but this forms a 3 plus ion. So we have 1 electron that we need to remove, and it has to come from the 3d7. So after we remove the 2 from the 4s and the 1 from the 3d7, we get a final electron configuration for CO3 plus of Ar3d6. And our last example is S2 minus. All right. So at sulfur, sulfur's typical electron configuration is Ne3s2 3p4. But in order to form a 2 minus anion, we have to add 2 electrons. And those 2 electrons, again, must go in the energy, or the subshell that is lowest in energy, that is only partially filled or not fully occupied. And so that would be the 3p, because there's only 4 electrons in there. Those 2 electrons have to go into the p orbital. And so an S2 minus electron configuration will be Ne3s2 3p6. But one thing that they didn't show you up here in the practice was the simple fact, or earlier was the simple fact that when you have a configuration that resembles that of a noble gas, you may represent that ionic electron configuration with a noble gas, like we did up here in cobalt, or I'm sorry, calcium. We're going to do the same thing for sulfur, okay? Argon has a configuration of Ne3s2 3p6. So it has the same electron configuration of argon. So we can simply put argon as our answer for this electron configuration. So let's look at gallium 3+, chromium 3+, and bromine 1-. Okay? So if we look at gallium, okay, we are going to have, oops, that needs to be upside down. All right, and dimmed a little bit. All right, gallium is going to have a noble gas configuration. We find gallium right here of Ar, okay, and then we're going to have Ar, 4s2, 3d10, 4p1. Okay? Well, sorry, that's gallium's. Gallium 3+ is going to have the following. Again, in order to have a 3+, we have to remove 3 electrons. And it's going to come out of this because it's the highest, and this. And so all that we're going to be left with is Ar 3d10. Let's look at chromium. Okay? Chromium, its initial one, it's right here. Right here. Okay, it's going to have argon, 4s2, 3d, and count here, 1, 2, 3, 4. Okay, 4s2, 3d4. But in order to get a 3+ charge, first we have to remove 2 electrons from 4s because that's the highest principal quantum number, and then we're going to have to remove 1 from there. And so our new ionic electron configuration for Cr3+ is 3d3. And lastly, bromine. Again, bromine is right here. It's going to be argon, again, for its normal neutral electron configuration. 4s2, 3d10, okay, across here, and then 4p5. Its ionic form is Br-. That means we have to add 1 electron. And the only place where we can add 1 electron that isn't already full is right here in the 4p. And so we get Ar, 4s2, 3d10, 4p6. Or we know what that is. If we go one more, add 1 more electron, our answer could also be krypton. So that is it for section 4. Hopefully you enjoyed this video. If you have any questions, email me or message me on Classroom. But please do not forget that you need to be working on your problem set. Your problem set will be due Tuesday evening on Classroom, giving you a little bit extra time, the first 4 sections. Now, sections 4 and 5 are not split up, but here's where you need to split up. You need to complete number 45 in your problem set and then stop. Do not go beyond number 45 after you complete number 45. Okay? So, with that being said, I'm going to sign off. This has been your Daily Dose of Doerfler. Have a great day.